Yo, what's up? What's up? What's up, everyone? It's your boy. It's your boy. Oh, oh. JOSHABRAHAM. We black. We back. Oh no. We back. Damn, that was a really bad slip up. But hey, analytical labs. Gotta prepare for analytical labs. Analytical labs. What about analytical labs? Basically, basically, I have an oral exam coming up. Oral exam. No, don't customize. I need to add more shit, bro. I got an oral exam coming up and I gotta prepare for it. So you know, Brent, you know. That's not a PDF? Yeah, that's a PDF. That's a PDF. So, yeah. 3, 4, 5, 6, 7, 8. Hello. Why is it not? Oh, fuck. Hello. Somebody just wrote the hi, and I'm gonna say hello to that hi. Hi. Hello. Hello. もちろんです。僕は名前はクラケトンです。僕は忍者。What? You're gay. Oh. Oh, whoa. It's all good. There's no wrong being gay. That's normal. What's so special about you revealing that you're revealing your interest on my chat? Like, what's the point? It's not special. That's what I was trying to say. Eight. Now we go to 7. Cool. How cool are we talking? Like minus 10 degrees cool? Minus 50 degrees cool? Hello, brother. Where are you from? Since your username is Hindi, I'm guessing we're almost from the same place. I don't know. I just realized that. Oh, okay. Well, brother, yeah, it's all good. Don't feel bad about it. Don't feel like you're better than everyone. That's what matters. You're just like everyone else. Nothing like, oh, you're just a normie. Nah, it's just it is okay. It is normal. It's nothing to be. You can. Hello, brother. I'm Ritik. Hello, Ritik. How you doing? Try on here, bro. All our swingers. Then we got a name called Swingers. That's crazy. Swingers. What's Maccabi? Let's go with that one. I think that's a better song. You can't hear the song, right? Oh no, YouTube don't copy strike. Okay, the audio is not hearable. 1, 2, 3 is not there. 3 and 4 is not there. Okay. I'm trying to goon too. Oh. Go to sleep, bro. Yo. I mean these. It's Okay, we got it all. Now I just need to order it. I need to order. I don't need to order. Okay. Okay, whatever you say, Notebook LM. It's not like you're the boss or anything. Nah. Okay. Notebook LM should work. Okay, I need your help with preparing for the oral exam. Did you know, again, that's not something very special you have to say. You feel me? Not everyone is gonna. Do you see straight people going like, "Oh, I like I like pussy. I like pussy. I'm gonna." No, bro, it's all good. You are normal. Don't worry about it. You don't need to prove yourself, okay? It's okay. It's okay. Okay. You need Kira justice. Is that an anime reference or something? I need your help with preparing preparing for the oral oral exam on oral analytical chemistry. Man trying hard to befit himself in a class of normies for justification. Whoa. Wait. Man trying hard to befit himself in a class of normies for justification. So you're like, this person is trying to be different. I mean, maybe, I don't know. But hey, it's okay. It's okay. You don't gotta push yourself onto others. If you feel me, you don't gotta just go everywhere and say, "Oh, I like." I hope you're trolling, because if you are someone like that in real life, oh, I will slap the shit out of you. No joke. It's a joke, YouTube. It's a joke. But yeah. Let's start with acid-base titration. Let's start with the acid-base titration. I have provided my lab procedures and the report Why do you advertise Restream? Do they pay you? No, they don't. But the thing is, I always remove the Restream reference on my landscape stream. Like from the description, I remove it, but on the vertical stream, I'm like, yeah, if you want, I could remove it. I also don't like the Restreams. I'm not a big fan of it. But yeah, just like I was saying, I do not value the vertical stream as much as the landscape one. Does that make sense? But hey, just so you noticed, I could start removing it. I need to, because I'm using the free version of Restream, and they, whenever I stream, they put their their link onto it. Watermark, or you could say description mark. So you might be asking, oh, why do you use Restream? Because I'm streaming on YouTube and Twitch at the same time through OBS. So, well. Hala, brother. Man, it's lagging. It's lagging? Still lagging? How does my hair, changing my hairstyle gonna... But is it still lagging? It's still lagging? Hello, brother. Hello, brother. How you doing, brother? To start your preparation for acid-base titration, we will focus on chemical principle, the necessity of standardization and specific procedures you followed. Core objective, the goal of this experiment was to determine mass percentage of acetic acid in an unknown sample solution by titrating it with a standardized sodium hydroxide solution. Sodium hydroxide is not a primary standard because it is a hygroscopic, and reacts with atmospheric carbon dioxide to form carbonates. Therefore, you must determine its exact concentration before using it to analyze your sample. Carbonate removal. Before dissolving the NaOH pellets, they are washed with a small amount of deionized water to remove any surface carbonate. The primary standard, you need potassium. The primary standard, you use potassium hydrogen thiolate to standardize NaOH. KHP is an ideal primary standard because it is stable, high purity, and has high molar mass. The reaction between KHP and potassium hydrogen thiolate. NaOH is 1:1. Yeah, result in your report. You determine the mean concentration. I don't care about my report. I just wanna. If my professor asks me, yo, spreading the word. What are your thoughts on Jesus? Oh, Jesus Christ, Lord and Savior Jesus Christ. I think Jesus Christ is a cool dude. Jesus Christ is incredibly cool. Oh, did I reveal my number? Does it matter? I don't think it matters. Determination of mass percentage of acetic acid in sample solution by titration with standardized sodium hydroxide solution. Okay. Uh, Preparation of an solution, approximately 1.1 grams of sodium hydroxide pellet. Why can't you just weigh NaOH pellets and calculate the concentration directly? It's not a primary standard due to the moisture and carbon dioxide absorption. Uh-huh. Yo, my computer is lagging like crazy. It is lagging. But is the stream lag? Is the stream lagging? I hope not. I hope not. Oh, sodium hydroxide is not a primary standard because it is a hygroscopic index. Are we cooking that NMR and spectrometers today? I'm not gonna look into organic chemistry today, where I have to learn about NMR spectroscopy. But where you go, did you write that chat thinking analytical labs means NMR spectroscopy? The things I did in my lab, which was related to NMR or something close to NMR, would be UV spectroscopy. I did UV spectroscopy and UV spectroscopy and one more, TLC. I don't have an okay. Infrared spectroscopy, okay. I got UV. I didn't get infrared. That's interesting. And I haven't done this one. NMR. I really want to try NMR. I really want to learn how to interpret from NMR. I'm still not there. Also, this is analytical labs. And yeah, I did not do NMR on my analytical lab. Why? Why? Because I think they're gonna make me do NMR spectroscopy during organic lab. I think that's when it's gonna come up. We'll do NMR this year. Uh huh. This year. So, are you doing any? Which course are you doing, gang? What do you do outside of studying? Yo. What do you mean by that? Like, What do you do outside of studying? I mean, weekend I have work. I have a part-time job at the restaurant. Yeah. I don't know. That's basically it, I guess. Maybe I used to go for bouldering, like rock climbing, indoor rock climbing. But then I got broke, and it's been a while since I went there. Grade 12. Okay, okay. Oh, they make you do those in the lab, in the school. That's cool. Mm-hmm. Makes sense. Makes sense. Oh, you get to do labs in your school. That's cool. Especially NMR type shit. Cool, cool. Oh, not the practicals. Oh, okay, okay, okay. I mean, if you go to university, there, if you go to university and you're gonna go specific into chemistry, etc., you are gonna do these practicals. Hygroscopic. I forgot what that is. Substance ability to attract water and water molecules. Reacts with atmospheric carbon dioxide to form carbonates. So sodium hydroxide reacts with atmosphere. Therefore, you must determine its exact concentration before using it to analyze your sample. Carbonate removal. Before dissolving the NaOH pellets, they are washed with small amount of deionized water to remove any surface carbon sodium remove any surface carbonate. Primary standard. You used potassium hydrogen thalate to standardize the NaOH is an ideal primary standard because it is stable, high purity, and has high molar mass. Stoichiometry. So first, titrate potassium thalate with a specific amount of NaOH. No. 1.1 grams of sodium hydrogen pellets were dissolved in deionized water, diluted to a. Okay, so that's where NaOH solution is prepared. Now 3 potassium thalate samples were weighed. Each was dissolved approximately 75 milliliters of deionized water in a separate Erlenmeyer flask. 2 drops of phenol phthalate indicator was added to each solution, and sample was titrated with the prepared NaOH solution. So we only had this much amount of NaOH solution. What? I need to take my. Oh, this is not my lab journal. Yo, where's my lab journal? I cannot. There we go. The lab journal. The Holy Grail. Okay. What did I do? Oh, it stinks. $50 milliliters of water, NaOH, 250 milliliters. So we have like 250 milliliters of 1.1 grams of NaOH dissolved. Then it's titrated with similar amounts of masked KHP. Okay, let's look at the part where you titrate or whatever, titrate Na 250 milliliters of NaOH with 3 different samples of KHP with different samples of KHP with what? And can you explain what's happening on a molecular scale? Also explain what is this indicator they're working and doing on a molecular scale. When you dissolve the KHP samples in water, the KHP dissociates into potassium ions and hydrogen phthalate ions. So cation, anion. The hydrogen phthalate ions act as a weak monoprotic acid because it has one acidic hydrogen atom attached to the carboxyl group. It acts as an acid, weak monoprotic acid. Okay. Titration process. As you add NaOH solution to the burette, it enters the flask as dissociated sodium plus and OH minus ions. On the molecular level, the OH minus ions from the NaOH seek out the acidic H plus protons. H plus protons on the hydrogen phthalate ions. They react instantly to form water molecules. Again, why couldn't the OH minus form with K plus? That could be a question. I could be asked that, and I don't want to be like, oh, but I think because hydrogen's better than potassium. No. Get the fuck out of here, bro. The door's that way. Get the fuck out of here. I think that's what the professor is gonna say. You stupid? You stupid, fam? A little bit. Stoichiometry. This reaction follows a 1:1 mole ratio. This means for every 1 molecule of NaOH added, exactly 1 molecule of KHP is neutralized. The equivalence point. This is the exact moment where every single acidic proton from weighted KHP sample has reached OH minus ion from the burette. At this point, the flask contains water, sodium ions, potassium ions, and phthalate dianions. The molecular mechanism of phenolphthalein. The indicator phenolphthalein is a large organic molecule that acts as a weak acid itself, and its color is determined by its molecular structure, which changes based on the pH of the solution. Okay. In acidic conditions, start of titration. While there's still unreacted KHP in the flask, the solution is acidic. In this environment, the phenolphthalein molecule remains in its protonated neutral form. Structurally, its atoms are arranged in a way that does not allow for a continuous path of alternating double bonds across. Oh, you know what? I want to see the structure. I want to see the structure. I pressed enter. Okay. Phenolphthalein in basic medium structure. Breaks this bond, forms a double bond, and this oxygen stays negative. Structurally, its atoms are arranged in a way that does not allow for a continuous path of alternating double bonds across conjugation across the whole molecule because it cannot absorb visible light in this state. It appears colorless. Structurally, its atoms are arranged in a way that does not allow for a continuous path of alternating double bonds across the whole molecule because it cannot absorb visible light in this state. Which state did you mean? Like conjugated state or at equivalence point as you add final drop of an OH, the neutralizes the last bit of KHP. Concentration of OH minus ions in the flask suddenly increases. Concentration of OH minus increases? How? I think it connects to inorganic chemistry at this point. Yo, from the unknown to known. The way was so long, but here I am again. Hello, brother. Yo, what's up? How you doing? Joe Rogan, and how is it going? New analysis. Not, yeah, there we go. Glittered Veronin. This guy's crazy. I gotta watch this channel once. As part of goatee, I need to watch this channel. Bro, my computer is getting slower. What's up, little guy? Stop slowing down, little computer. I know you're running a lot of stuff in the background. But come on, just work. Like, it's not that hard to work. Just work, okay? Molecule remains in its protonated form. Structurally, its atoms are encoding overloaded. Consider turning down. I mean, what's the settings right now? Come on. What are the encoding settings? Like, it should not be this slow. Stream. No, appearance. Video. Output. Apple VT hardcore, yeah? Rescale output 990 1080p. Okay. FPS is 30. Okay. OpenGL rendering. At the equivalence point, I need to get a little bit more info on this part. I need more info on this part where the number of OH minus ions increases. Let me read the rest of I also need to know which structure exactly is the one that does not absorb light and remain. How is the conjugation or the resonance of the structure helping in that? Also, how is that resonance lost when it's at equivalence point? These excess OH minus react with the phenolphthalein molecule, stripping away the proton H plus. This deprotonation causes a rapid structural rearrangement of phenolphthalein molecules. The molecule opens up into a planar structure that creates a large extended system of conjugated double bonds. This extended conjugation allows the molecule to absorb green light and emit pink magenta light. The persistent pale pink endpoint you look for is the molecular signal that you have added just a tiny excess of base, usually only a fraction of a drop, indicating that KHP has been completely consumed. Why the 250 millivolumeters? Okay. So think. I had one more doubt. The doubt uh, where why the K plus. Also, why is the OH minus from Na attacking the H plus attached to the compared to the free cation potassium? Oh, it's gonna take some time. Oh, it is working. It's working. Okay, it's working. To understand what is happening at the molecular level during your acid, the sudden increase of hydroxide ions during the titration of potassium hydrogen phthalate, you are adding a solution of NaOH before the equivalence point. As a drop of NaOH enters the flask, OH minus immediately attack the acidic proton of the hydrogen phthalate ions to form water. Because of these, OH minus are consumed instantly by the reaction. Their concentration in the flask remains extremely low. At equivalence point, you reach a 1:1 molar ratio where number of moles of KHP equals number of moles of NaOH. At this precise moment, every available acidic proton from your weighed KHP sample has been neutralized. Hi, hello. The very next final drop of NaOH you added provides OH minus ions that have no more acidic protons to react with, because there's no longer a sink of these ions. The concentration of free OH minus in the solution spikes instantly. This sudden change in the chemical environment is what triggers the indicator. Phenolphthalein colorless versus pink structure. The sources confirm that 0.5% phenolphthalein solution, which transitions from colorless to a persistent pale pink to the endpoint, while the specific molecular diagrams are not in the provided structures. The following explains the chemical principles of that transition. The colorless acidic structure. In the acidic environment of KHP solution, phenolphthalein exists in its neutral protonated form, often called as lactone form. Okay, let me inner peace, inner peace, inner peace. Calm down, inner peace. What's going on? Why are you slow, Cap computer? What's going on? I'm not running too many tasks. Is it too many Chrome Safari tabs or something? No. That's all I have. That's all I have. There's not even too many tabs open. Like, what? Apple, you need to step up your game. Like, come on, this thing is slow. Buy a new MacBook. I'm saying you gotta make this machine faster. I don't want to spend money. Let's go to activity monitor because this shit's not it. Why is it so slow? What the fuck is going on? What is consuming this much CPU? Windows Server. Okay. Skylight framework. Okay. %22 of CPU OBS. Okay, 22. But where's the rest? You're still only using 30% of the GPU. CPU, not GPU. What about CPU? CPU percentage. ChatGPT is using 103. 103. GPT, you gotta go. I'm sorry, you gotta go. Get the fuck out of here, GPT. I did not know you were taking that much. Now is it free? OBS is using 48. I can live with that. So the GPT was the problem? Neutral form. Oh, I need this image, please. Can I get it? 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 Can I hit it? Can I hit it? Oh, come on. You're still slow. Kernel what? 332 gigabytes. Virtual memory size. What? What is that? It's not even clear. So phenolphthalein indicator, when it's colorless, it has this bond. And when it's when it's even lower pH, it goes to alcohol group is attached. Interesting. Otherwise, it's negative anion. So no minus. Okay. That happens because the OH minus absorbs H plus from the phenolphthalein indicator. I need to get some water. Some water. Oh shit. Just a minute. Bello, where are you? I'm here. I'm right here. Don't worry. I'm like right here. Damn. Monk vase. In this state, a central carbon atom in the molecule is bonded to four different groups. This prevents a path of alternating double bonds from extending across the entire molecule. The role of conjugation and resonance: for a molecule to absorb visible light and thus appear colored, it usually requires a large system of conjugated double bonds. In this colorless form, this resonance is broken or localized into separate parts of the molecule because it cannot absorb visible light. It appears colorless to your eye. For a molecule that absorbs visible light and thus appear colored, it usually requires a large system of conjugated double bonds. In this colorless form, this resonance is broken or localized into separate parts of the molecule because it cannot absorb visible light. It appears colorless to the eye. I did not exactly get why exactly it was it colorless. Transformation of equivalence: when the final drop causes the OH concentration to spike, the OH minus ions strip protons from the phenolphthalein molecules. This causes a ring opening structural rearrangement. The central carbon changes its bonding, allowing a bridge to form that connects the resonance system of the three individual rings into one giant continuous path of conjugation. Ions strip protons from the phenolphthalein molecules, causing a ring opening structural rearrangement. The central carbon changes its bonding, allowing a bridge to form that connects the resonance system of the three individual rings to a one to chain one. What? What are we talking? Bro, why is it so slow? Why is everything slow right now? Oh no. Oh man. For a molecule to absorb visible light and thus appear colored, it usually requires a large system of conjugated double bonds. In the colorless form, this resonance is broken or localized. Okay. Gaining color. This newly formed large resonance system, the quinoid form, is now capable of absorbing green light, which results in the pink magenta color you see in the flask. Why OH minus attack H plus instead of K plus? You asked, yeah. Thermodynamics of water formation. The reaction of OH minus plus H plus water is one of the most energetically favorable reaction in chemistry. Okay. The OH minus ion is a strong base with a power affinity for H plus proton in the hydrogen phthalate ion. Spectator ions, the potassium from the KHP and the sodium from the NaOH are spectator ions. They're already stable, fully dissociated cations in water. No reaction path. OH minus and K plus do not react to form a new compound in an aqueous environment because KOH is a strong base and that is 100% soluble and dissociated. There is no chemical reward like the formation of stable water molecules or precipitate for OH minus to interact with K plus. Therefore, OH minus ignores K plus and specifically targets H plus to create stable H2O molecules. The specific names of the phenolphthalein structures and specific sp2 sp3 hybridization of the central carbons are based on the general chemical principles of the indicator behavior and not explicitly detailed in the provided laboratory reports or SOP. Okay, I get it, but I could be asked. Okay, I kind of understand the thermodynamics of water formation. It is thermodynamically more favored. It is energetically more favored to form water if OH minus exists. I also need to know. Wait, NaOH with water. So when you answered this part, I'm guessing the K plus and the Na plus are already surrounded by H2O, where the O minus O lone pairs O are surrounding it. This is what I hate. I hate taking time. I have one more question where I understood where if we talk about theoretical equivalence point, then you cannot actually you will start your organics from tomorrow. Like, is it like a self-study or your classes? Yeah. So if I understand, at theoretical equivalence point, the phenolphthalein does not actually form pink color. Because if we go head to head as OH minus reacts with phthalate anion, there's not going to be any. If the OH minus reacts with exact amount of phthalate ion, then there's not going to be any OH minus to react with the indicator, so the indicator can show the color. So if we think about it, the indicator can only show the color if the amount of NaOH is a little bit higher compared to equivalence point. Do you think I know something of math and chemistry? A little bit of knowledge is all I have, maybe. I mean, hey, from what I understand, we can keep on improving. The more you learn, the better you understand. And the more I look into the same topic I learned, there's new stuff coming up. So, yeah, you can always improve. You can always improve. You can always. Again, Vaibhav, I gotta say one thing before. At night times, people start to yap a bit higher. What are you studying in organic right now? I'm studying reaction mechanism, especially substitution reaction, more specifically how solvents affect a substitution reaction. I still haven't cleared it. I'm still having a lot of doubts, especially I cannot pinpoint. I know how protic solvents speed up SN1 and slows down SN2, but I still haven't looked into how aprotic solvents affect SN1 and 2. So I need to understand a bit more on that. Then I'm gonna move on to rest. SN1 and SN2, yeah. I'm still SN1, SN2. So it's energetically favorable. When you say energetically favorable, that means after the reaction there's more higher entropy. Yeah, that should follow laws of thermodynamics. What else could it mean? Energetically favorable. Higher entropy, that's the first thing that comes to my mind. What else? Negative. Is this an endothermic? It's not an exothermic reaction. But still, it could be a very small exothermic reaction. At least it should have a negative Gibbs free energy. I need to ask that. This prevents the path of alternating double bonds. Polar aprotic solvents are the ones that do not form H bonds and have non-zero dipole moment, so the salts are dissociated in them. Yeah, I read that. I read that the salt or the reactant that is added to the solvent dissolves. But again, what was I confused? No dipole moment. The salts are dissociated. Dissociated as in they separate into anion cation and exist in the solvent. Also, I should also get an example of aprotic solvent because my mind is not coming up with any. Example of aprotic solvent. Acetone. So when aprotic solvents are in water, how do they be? This means they have strong, uneven flow of electrical charge across molecules. So since there's no H bonding, the solvents have excess electrons, thus attacking reagents are more prone to act, and as a result it favors SN1 substitution. No H bond is there. The solvents have excess electrons. There's no H bond. Solvents have excess electrons, thus attacking reagents are more prone to act. Just attacking reagents are. Solvent has its excess electrons, so solvent is basically negative charged. If they are negative charged, it could hinder the nucleophile, no? Solute. Wait, the solute. If we are talking solute, if I understand, the solute is basically the reagent, right? Or reactants. That's the solute, right? And solvent would be the polar aprotic solvent. So the polar aprotic solvent does not have any hydrogen bonding. And from what you said, the solute has excess electrons. Absolute heavy. They mainly solvate cations. Oh, aprotic solvents solvate the cation. So it gives it kind of lets the anion open, but again, my stupid mind is saying anion. Anion is negative. How is nucleophile gonna attack a negative anion? That's my mind. That's what my mind is telling me. But I'm guessing there's an answer to it. I know there's an answer to it. I'm still having a little bit hard time picturing the whole polar aprotic solvent and the reagent. Okay. The OH ion is strong base with a powerful affinity for H plus proton on the hydrogen phthalate ion. It's one of the most energetically favorable reactions in chemistry. OH minus ion is a strong base with a powerful affinity for H plus. What was going to ask here? Yeah, okay. So if I understand what being energy favorable, then that should mean, if I understand what being energetically favorable, then that should mean the resulting water should provide more entropy to the system, just like that. I don't know if it's exothermic reaction, but it should be negative in the Gibbs free energy See, if there's a F minus ion inside the protic solvent, the H atoms would surround it because the fluorine is more electronegative, and as a result, fluorine cannot attack or substitute any other compound. Yeah, that's how fluorine gets stuck in the protic solvent, and I think that's how SN2 reaction is less favored in protic solvent. The nucleophile gets stuck. But for aprotic solvents, since there's no H bonds, that F minus ion is free to substitute any other cationic part in any other compound, making them more prone to SN1 reaction. That could still that goes for both SN1 and SN2 if I read that right. It just provides easy access for the nucleophile to attack the reagent. Or am I stupid? Am I missing something? The provided sources focus on the procedural, stoichiometric, and statistical aspect of your titration as one is to one reaction. However, they do not contain the specific information. I don't give a shit if it contains. Just let me know if I'm right. The following explanation is based on the general chemistry principles from outside your sources. For your reaction to be energetically favorable or spontaneous, the charge must be negative, not positive. As a spontaneous reaction in your titration, as soon as a drop of which is clearly short enough. Exothermic nature, the reaction between. For SN2, we need such an ion to attack the anti-bonding orbital, which fluorine sure can do. There's inversion for SN2 reactions. So aprotic solvents just makes the reaction faster, or is I feel like aprotic solvent does not even affect the speed of reaction because it doesn't do anything. For SN2 we need such an ion to attack the anti-bonding orbital, which fluorine can sure do. So a high electronegative ion. There's inversion for SN2 reaction. What you mean by inversion? Like, I'm having a slight doubt on that part. Exothermic nature. The reaction between H plus and OH minus is highly exothermic, meaning it releases heat. When the strong bond of water molecule forms, a significant amount of energy is released into the surroundings. In a standard lab titration like yours, the amount of acid and base is relatively small, so the temperature rise is usually not noticeable. It is exothermic, okay, without a sensitive thermometer, but the energy release is a major driver for the reaction. Entropy. Your intuition about entropy is correct, though the reasoning is interesting. Interesting? What? The hydration shells, as discussed previously, H plus and OH minus ions in water are not free. They are surrounded by highly organized shell of water molecules. This organization represents a state of low entropy. This organization represents a state of low entropy, okay? When H plus and OH minus react to form a neutral H2O molecules, these rigid hydration shells are broken and water molecules are released back into the bulk liquid, where they can move more freely. Okay. This unordering of solvent molecules causes a positive change in entropy, which helps make the reaction even more favorable. In summary, reaction is favorable because it is exothermic and increases the entropy of the solvent, leading to a large negative delta G. Okay, so I got that part. I'm just there's only one more part that I would like to just clear out. Okay, let's move on to the next part, but before that I need some explanation on how the indicator does not absorb any color initially or in the neutral / slight acidic environment, then followed by what? Followed by addition of a little bit excess OH minus, resulting in the change in structure, and now suddenly it can absorb light. Could you explain to me what exactly makes it absorb light and what makes it not absorb at all? In your acid-base titration of acetic acid and standardization of sodium hydroxide, the indicator used was phenolphthalein. The shift from colorless to a persistent pale pink is a result of dramatic molecular transformation that changes how the molecule interacts with light. Okay. your acid base, acetic acid, did I ask that question? Okay. The shift from colorless to pale, dramatic molecular transformation that changes how molecule interacts with light. The following explanation regarding the molecular, orbital behavior, and structural conjugation of phenolphthalein is based on general chemistry. In your slightly acidic environment created by potassium hydrogen phthalate or acetic acid sample, phenolphthalein remains in its colorless protonated form. Structure at this pH, molecule has a central carbon atom. Oh, come on. At this pH, the molecule has a central carbon atom that is bonded to 4 different groups. The molecule has a central carbon atom. Let me pull up the structure. No. No, what the fuck you doing? Okay. This is the phenolphthalein that I am getting, colorless. Fragmented resonance. In the slightly acidic environment created by the potassium hydrogen phthalate or acetic acid sample, the phenolphthalein remains in its colorless protonated form. At this pH, the molecule has a central carbon atom bonded to 4 different groups. It is an sp3 hybridized. Is this the central carbon atom? Electron behavior. Because of this tetrahedral carbon, the electrons in the 3 surrounding benzene rings are trapped within their individual rings. They cannot flow from one ring to another. Okay. Is it benzene? Yeah, it's benzene. Light absorption. For a molecule to absorb visible light, its electrons must be able to jump between energy levels that is relatively close together. Because the electrons in the phenolphthalein are restricted to small isolated areas, the energy gap they must jump is very large. This requires high energy ultraviolet light. Since the molecule does not absorb any light in visible spectrum, it appears colorless to human eye. Oh, okay. But here also it's not like all the rings are opened. As you reach the equivalence point, OH minus ions from the NaOH titrant have neutralized all the available acidic protons in your sample. Then very next drop, deprotonation, OH minus strips away the hydrogen proton away from the phenolphthalein. The loss of these protons causes entire molecules to undergo a snap into a new shape. The central carbon atom changes its bonding and becomes planar. Okay, it only have three bonds. New structure is called quinoid. Is it named here? No. This is a state where the molecule suddenly gains the ability to absorb visible light. Extended conjugation. The structural change opens a bridge between 3 rings. This creates a large system of conjugated double bonds. Alternating single and double bonds extend across the entire molecule. So there's this double bond, and that could be here or here. This connects the entire molecule. visible light absorption. This large track of electrons significantly lowers the energy gap required for an electronic transition. The energy needed to move an electron now falls within the range of visible light. This track of electrons okay. Okay, I need to ask this part. So this energy to move from okay, now the energy required for atoms to excite is now lowered because I guess it's because what? Because there's a structural change where the carbon changed from sp3 hybridization to sp2, and there's the double bond shared between each benzene ring, so the electrons inside the benzene ring could also travel to other parts, thus resulting in an overall connection of electrons. Again, my wordings are so bad. Summary for your exam. Colorless electrons are isolated in small areas of the molecule. The energy gap is too high for visible light. Only UV is absorbed. Excess OH minus causes a structural shift that causes an extended conjugated system. This lowers the energy gap, allowing the molecule to absorb visible light, which we perceive as pink. Okay, one more thing. So, in this case where the central carbon has changed its hybridization from sp3 to sp2, and in the structure I see a double bond between one of the benzene ring and carbon. If I understand resonance, this double bond is gonna be shared across other this double bond is going to be shared across other benzene rings, and thus connecting the electrons inside the benzene ring, and this so-called connection brings down the what's the term though? Energy gap for the absorption light, thus letting visible light to be absorbed. Shut the fuck up. Is it correct? The sp3 and sp2 transition of the central carbon. Your observation is the colorless state. The central carbon atom is sp3 hybridized, meaning it has 4 single bonds arranged in a tetrahedral shape. This geometry acts as an insulator, physically blocking the pi electrons of the 3 benzene rings from interacting with each other. At the equivalence point, when you add the excess OH minus required to reach the endpoint, resulting structural rearrangement causes the central atom to be sp3 hybridized. sp2 hybridized. This makes the center of the carbon molecule planar. The resonance, you correctly identify the newly formed double bond between the central carbon. The connection once the central aligns with the p orbitals of the 3 surrounding rings. Delocalization. The alignment allows the electrons to delocalize, meaning there is no longer restricted to single benzene ring as you suggested, the double bond effectively spread across the entire molecular framework, the electrons can now travel along this extended path of alternating single and double bond extended conjugation. Extended conjugation, that's a good term. Lowering the energy gap and light absorption. The reasoning regarding the energy gap is fundamental principle of physical chemistry. Okay, I kind of understand now. I get it. Okay. Now, 25 milliliters of aliquots of acetic acid sample were transferred into Erlenmeyer flask. 2 drops of phenolphthalein indicator was added. Each sample was titrated with standardized NaOH solution until the persistent pale pink endpoint was reached. Okay, so first we add KHP, and from the number of moles of KHP, we find the number of moles of NaOH added, and from that we get the mean concentration of NaOH that is absorbed by the KHP, right? Yeah, something like that. Okay. I'm gonna play some video games. Yeah, I'm done for today. Maybe a little bit of recipe, and I'm gonna peace out. Peace out, YouTube.